Superstar Astronomers is a members-only broadcast which features talks from the world's leading astronomers. Coming up later this month, we will be hearing from Dr. Emily Levesque about a bird that mimicked a black hole and a telescope that got shot. Are you curious what on earth that's about? Because I am. If you are, just like me, please visit our website to register for the webinar and find out about it for yourself. Also, new this year, our very own Sebastian Otero is hosting a very exciting webinar series in Spanish. So if you or one of your astronomy friends speak Spanish, please feel free to join us. The links to learn more about each of these webinar series are up there on the screen. Finally, we would like to thank and acknowledge our sponsors, Voice Astro and Chroma Technology. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. This broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation and surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy. Okay, now with that out of the way, allow me to introduce your instructor for today. It is my great pleasure to welcome back to this webinar series, Richard Berry. Mr. Berry has been a frequent presenter at past AAVSO meetings and webinars, and it's really not hard to see why. He has over 30 years of expertise in a wide variety of fields, from telescope making to observatory building to photometry, which he's been practicing ever since the days of photomultiplier tubes. As if that weren't enough, he's also a software developer and the author behind the software Astronomical Image Processing for Windows, also known as AIP for Win. Between his observational experience and his experience literally writing the tools that the rest of us use, he's come to be quite an expert on the topic of photometry. Not only how the data is recorded, but also how it's handled behind the scenes. Today, he's here with us to give us a glimpse into the nuts and bolts of photometry and how, with a little bit of math, a bunch of pixels can be transformed into scientific discovery. Without further ado, please allow me to introduce Richard Berry. Welcome back, Mr. Berry.
Hi, Lauren. So what I'm going to do today is take you on a tour inside the computer, inside the way it works. I will be using AIP for Windows as my demonstration tool, but basically all photometry, all aperture photometry works pretty much the same way. So what I will tell you will probably apply reasonably well to almost any software you may be using. So I'm going to share my screen, and if we've done this right, we should be there.
Looks great.
Okay, and okay, so, and I'm using the presenter mode, and if everything's working right, you guys are still seeing the title slide.
Yep, looks great on full screen and everything.
We practice and we're perfect. Okay, thank you. Wait a minute. Oh, it's a very Windowsy thing. It locks out my screen. Okay. Okay, so AIP for Windows is free, and that's by accident. My publisher went out of business and left my software orphaned on the web. I did some quick hacks in it and created a groups IO called AIP for Win user community, and you can download the software from there. It's free, it's open to everybody, and with all honesty, it does have some bugs, because it was a quick and dirty job. So let's begin the software. um, I'm going to be working with today 2 images of M67, which is a cluster that's used for standardizing filters and cameras, because it's got a lot of stars whose standard magnitudes are well known. And I will be demonstrating today with the very simplest photometry tool in AIP for Windows, which is a single star photometry tool. This is basically written as a learning tool for beginners. And I'm demonstrating with it because it's not complicated. It's easy to explain. So we click on that link. The tool comes up. You can see it. Let me get my laser pointer. There we go. So there's the tool. It's a very simple tool. And we go out and we click on a star, and a magnitude comes up. Aha, it's magic. Okay, so what I'm going to be talking about today is how does that happen? And we're going to be moving in close and getting really up close and personal with the pixels and the star images. Now, this image is a 4-second exposure using a AAVSO by Unistellar. Its basic way of taking pictures is it shoots a lot of 4-second exposures and then stacks them. The other image I'll be working with is a stacked image that's made with 900 4-second frames. And when you do that, you get a beautiful textbook star image. I mean, there's the star. It's nice and well sampled. You've got pretty clean. There's not much many background stars in it. And you can see, because we're working in M67, it's a very crowded field. This kind of field, it kind of gives photometrists conniptions, because if you go click and you want to do something with this star, you're going to have some competition with that star. But we'll talk about how that kind of stuff works. So here's the basic piece of information that anybody who does photometry, aperture photometry, needs to understand. This is how we slice and dice the image of a star. Okay, in the middle, closely surrounding the star, is what's called the aperture. Aperture is the Latin word for window. Okay, and it contains most or all of the light in the star image. Then we have a gap. And the reason we have a gap is that the star image usually has some extension. There's light out here. And it turns out, this is interesting, that the most efficient photometry actually does not quite use all of the star's light. As we begin to add more pixels to try to get all the starlight, we're adding noise from the sky background. And then finally, we have the annulus, a donut or a bagel. You can call it either one if you want to, which we're going to use to determine how much light is coming from the star that is adding to the light in the star. So the definitions, this is the aperture radius from the center out. This is the inner annulus radius, and this is the outer annulus radius. And because we're going to be talking about software code, and if you don't do software programming, I'm not going to get technical, but you will see code. Don't let your eyes glaze over. It's to make a pun, it's basic. Okay, so it's basic software. We call any given pixel the terminology we use is FP. FP is an array of floating point values, and XY is its XY coordinates, so X and Y axes. So the image itself is FP. This notation means it's an array, and XY tells us which pixel it is. And we'll also be looking at another way of looking at the star image, which is to create a profile. Okay, and in the profile, what we do is here's our aperture, inner and annulus, inner and outer annuli. And these, in this graph, we're moving radially outward and plotting each pixel. So this pixel here, which is at about a radius of 2, gets plotted here. Okay, so if you look at the lines, it'll be like 1.5 or something like that. So, and then a pixel out here, which is quite far from the center of the star image, it will get plotted out here somewhere. And you can see then that the star has a profile. Okay, and that profile is characteristic of every image in the star. And you can see out here that the annulus, it's clean as a whistle. This is absolutely beautiful. We love it when there's no other stars hanging out here to mess up our measurement of the background sky. And you'll notice, if you look carefully, that there's still a little bit of starlight out here in the gap. Okay, and you can see that too. You can see these gray pixels. So we will be using the profile as a diagnostic for whether we're getting good photometry. So I'm going to start out. Okay, if you do photometry, you've all seen this kind of stuff. Okay, here's your 4-second exposure, and there's the star. And here we have integrated for 900 seconds. And now you can see, yeah, the star is really there. Okay, and you can see that the other stars, in the 4-second exposure, these guys look pretty solid. In the 900-second exposures, these guys are really, really solid because we've averaged so many photons together to create this image. You can see the sky background is almost noise-free. It's really, really nice if you can integrate for long periods of time. And then I'm going to show you a couple more cases of how star images develop. Okay, here's a comparison of a 4-second exposure and a 900-second exposure. Okay, this guy here, which is nice and solid in 15 seconds, you can't be sure it's really there. You look at something like this and you say, what's that? Well, that could be a cosmic ray. It could be a hot pixel. It could be anything. When we look at it after 900 seconds exposure, it's not there. But this image here, which is probably this little cluster of pixels, is there. Okay, and we can see another faint star and how it develops. It's useful in learning photometry to play around and compare what kind of images you get with different kinds of exposures. So you get to know at a sort of a gut level what good photometry looks like. So here is a 13th magnitude star. Here's a 14.5 magnitude star. Here's what the star looks like as we're getting down to 15th. And here we are down halfway down 15th magnitude. With this little telescope, which has an aperture of 114 millimeters, you can work reasonably well to 15th magnitude, and in a pinch, you could be going down to 16th magnitude. So we've looked at some stars now, and I'm going to talk about the facts of life when it comes to talking about star images. This is a birds and bees of stars. Okay, the star, and this will sound maybe a little overly academic, but when you're a computer programmer, you don't look at the star at the image and say, that's a star. Okay, it's a cluster of pixels that are brighter than the average of the sky. That's all they are. And remember, pixels are just numbers in an array, and that's how we're going to treat them. Non-stellar artifacts can look a whole lot like star images. You always have to be aware that there's cosmic rays, that there's muons flowing off of the cover glass on your CCD. There's all kinds of things that can make things that look a lot like a faint star image. Every pixel is noisy, okay, because it's not just a magic number that happens. It happens because photons flowing in randomly vary, and the variation is uncertain by approximately the square root of the number of photons that happen. So if you have 10,000 photons coming in, it's going to be 10,000 plus and minus 100, square root of 10,000. Okay, the sky background light is added to the star light. Okay, the sky background itself is noisy. It's again photon shot noise. And when you look at these images, you always see those that randomly look. If we ran a movie of a series of frames like that, it would look all swarmy. It would look varying up and down crazily. The sky background always contains faint, hard to see stars. Okay, there's always parasitic stars in your background. And what they do is they make the background brighter. Now you can say, well, on the average, there's going to be a faint star underneath your bright star, which is perfectly true. But you're going to be, every time you do photometry on that star, you're going to include that faint star in it. What we don't want is to have the light of the sky background included every single time. Okay. All star images blend gradually into the sky. They do not have hard edges. Okay, they fade away. And if you do a really long exposure, you can find star pixels out 10, 20 pixels away from the center. In any given image, all star images have the same profile. Okay, this is contrary to what your visual, the way you see it visually. It looks like bright stars are big, faint stars are little. They all have the same profile. In other words, a bright star spreads out quite some distance, so do the faint stars. Bright star images are not bigger than your dim stars. And when you're doing photometry, shoot your darks, shoot your flats, calibrate your images, because you would like at least to get your pixels all normalized to the same sensitivity, and you'd like to get rid of hot pixels. So I'm going to, beat on this a little bit. This is star image profile constancy. In other words, here's my 4-second exposure, here's my 900-second exposure, and I've got this little trio of stars. And they begin to show you how you work with the profile too. Okay, so here's your profile. It comes down in the 4-second exposure, it looks like this. In the 900-second exposure, it looks like that. It's exactly the same. We're picking up here in the annulus, you can now see we're picking up light from this star. Okay, and this happens. The takeaway lesson here is that whether it's a 4-second exposure or a 900-second exposure, the profiles are the same. Now that's a bright star. For a medium bright star, once again, the profile is here, the profile is here. And now this guy, he's picking up that guy. And you can see the annulus is highly compromised. It's got a lot of background starlight. But if you look at it, that star is only maybe 10% of the total amount of light that's coming into the annulus. If we can figure out some way to get rid of those, we'll have an accurate level, background level that we can subtract. Now here's our gap again coming in handy, and you can see that there's some light in that gap. But look at this carefully and you can see, we have chosen our aperture radius so that we get very, very little parasitic light. And that's what we want to do. And it should be perhaps obvious by now. A corollary of this is you're going to shoot your bright stars and your faint stars. You're going to shoot everything with the same aperture radius and annulus radii if you want consistency. Because if you change this, you're going to be getting more or less light from that star, and you're going to be getting more or less light from parasitic sources. And then look at this faint star. Okay, well, here is your profile again. Okay, here it is in the 4-second exposure. It's messy. And here it is in the 900-second exposure. And you can see now you got the parasitic light from this guy, and you got the parasitic light from this guy. And you can say, well, but that profile is there. And this is why you want to keep that constant, because you're trying to make your photometry the same regardless of the exposure. Because even though it doesn't look that way, when you analyze it technically, it turns out to be that way. So we're going to click on it. We're going to walk through the process now of what happens when you click on the star. So I've talked about stars, and I hope that you will you will bring up your star images and blow them up to 800 or 1,000 or 1,600% and look at your stars carefully. So you begin to understand it's down at the pixel level that photometry happens. So we're going to click on a star, and in computer lingo, my click generates an event. In GUI type programming, it's called mouse up. Actually, it creates a mouse down, and then a mouse hold, and a mouse up event. Okay, we're going to trigger on the mouse up event, and the mouse up event, we grab the XY location of where you clicked. Now we're going to dive into the software, and bingo, you clicked there. Click. Okay, here's the star you want, a photometer, but your hand shook a little bit, or the software, which is looking at 500 images in a row and the stars are moving around a little bit, or your tracking wasn't perfect, you're going to have to follow that star. So the software thought in the 399th image that the star was here, but in the 400th image, the star had moved over to there. Okay, so this was your starting point. You went click. And here's what happened. The software figured out where the darn star went. Well, this is really handy because, you try to put your mouse on the right spot and click there. You can do that pretty well. But you can't do it at 100% typically. You really do need to magnify it the way we've done it here. Okay, now we're going to dive into computer code. And I've done this very slightly kludgy stuff here because the code I'm showing you and the code that was generated that image is not exactly the same. Okay, but if you're allergic to computer programming, I'm sorry, but this is it's like lifting the hood and looking at the carburetor and the distributor and the battery and the radiator and all that stuff that's under the hood. So this is the code that generates, this is my click, and we get an X and Y value. And we then run code that determines where the center of light is, and it draws the circles. So it draws a white circle and 2 yellow circles. Okay, so there's the white circle and there's the 2 yellow circles. Then the code here says, okay, I've just figured out where the center of the star is. And then it runs it again. Okay, this time on the result that has come out of this first centroid effort. So now we run it again. Now we're centered and it draws them again. So this is your first time that piece of code runs, right? And it just draws the circles for the click. Then when you get that second one, it zeroes in on this guy. Now, where I've kludged a little bit is in this drawing, I don't show it, but we sneakily are going to change the aperture so that the aperture is actually here. It's smaller. We're looking at a smaller area. Okay, so now I'll introduce another programming concept if you're not familiar with code, and that's called a function. Okay, and that's what we did here. This we called in the current document, we called the function star centroid, and the code is here. And the first thing it does is it says, okay, these are the things that I'm going to put into my computation. First of all, I'm going to put the image in. Then I'm going to put in diaphragm radius. That is the aperture radius, because we use, okay. And I'm also going to put in my click value for the centroid. And then remember, the software does not know where that click came from. Okay, it doesn't know whether there's even a star there, because we don't use the centroid function only in this instance. We may be using it in some sort of automatic tracking routine. So the first thing we want to do is we want to define an area that runs from the first XY to the last XY. And we also want to make a check that the area that we're going to analyze actually lies inside the image. Okay, so the image runs from X max to Y max. I mean, X max, Y max to Y max to X from, it goes from, sorry, let's get this right. It goes from X min to X max and so forth. In other words, it's inside the image. That's a check. It's a necessary check, because if you don't do it right, you can get horrible things like divide by zero and boom, the software crashes. So my click was here. The code runs and it defines this region from FP first X to FP last X. Now I've sized this region to be bigger by a small amount, by in this case 2 pixels, than the aperture that I'm going to be looking inside. Okay, and this is where my click went in. Okay, and it's useful. You don't, for this to work well, the initial click does not have to be accurate. That's why we're doing the centroid stuff, because when we're going to do the photometry, we really want to know exactly where the star image is. So the next thing we do, let me back up a little bit. Okay, whenever you see a structure like this, for X equals first to last, and you'll notice this for X equals, and then there's a next X. This is a loop. So the software is going to go around and around and around, and it's going to do this routine inside for each one of those. So what it's doing is it's scanning down the image and checking, and it's doing a calculation. Is this pixel inside or outside? If it's inside, we're going to add its value to the total, and we're going to add the number of pixels. We're going to increment that by 1. So what I'm doing is I'm computing the total, the average value of the background, the star sum, divided by the number of pixels. And then I'm going to compute a threshold value, something that's a little bigger than the background. It might be 20% brighter than the background, or 2% brighter than the background. This is something that the programmer determines by trial and error what gives good results. So this is secret number that's hidden inside the code. So we're going to get a background and we're going to get threshold. So that's what this routine did. It produces these two values. Okay, now programmers in the audience, you're going to say like, well, wait a minute, you have this loop again and again and again. That's a very inefficient way to code this kind of work. And the answer is this code was written to be very easy to explain to myself. So I could be sure when I was writing this, that it actually did what I wanted it to do. And you say, well, wait a minute, you're writing it, you should know what it does. That's called bugs, okay? It's very easy to get clever and end up doing something like computing a background or a threshold that are not right. Okay, every programmer knows that. They don't like to admit it. You make mistakes. So this code, which is very easy to explain to myself, is also relatively easy to explain to non-programmers. So I'm doing something that's redundant and slow, and my excuse is there's like 250 pixels here. It did that in literally microseconds. The human being's time scale is the 10th of a second. So you don't see the fact that I've written very, very inefficient code. Okay, so what I've done here, just to clarify what's going on, if a pixel exceeds the threshold, I've colored it red. Okay, so here's the star image, remember him. Okay, and you'll see that there's a bunch of other pixels that exceed that value, and here's what the centroid value was. So I've scanned this whole region. I found these guys that are bigger than threshold. And now, you know where we're going. We're going to take an average of these ones that exceed the threshold and say, well, that's where the real center of the star is. But these guys that are out here hanging around, they're going to throw my value off by quite a bit. They're going to move it somewhere in this direction. And I don't want that to happen. So I'm going to apply a test, which is called the neighbor test, which is how many other pixels in the star image does each pixel touch? Okay, well, these guys are above value. So, okay, and here's what that looks like. Once again, we're going to scan through the whole thing. We're actually going to do that test again. Okay, so we got a computer standpoint, we've got a lot more numbers to crunch. But again, computers are so fast today. And for each pixel, we're going to check and see how many neighbors it has. So we're going to look at pixel XY, and we're going to look at the pixel below it, above it, to the left, to the right, diagonally, and we're going to say, if it has more than 3 neighbors, count it in. Okay, measure 2 things. One is its distance and its value, its pixel value. So this is where we do that. And we're subtracting the background skylight off. So if a pixel can pass the neighbor test, it's going to be in this cluster. Remember I said star image is a cluster of pixels? Okay, and what we've done is we've said, aha, these guys are here. These guys do not pass. And I added a couple samples here to show you. Each one of these guys has 2 neighbors. They don't count. They're not part of the star image. Now, in aperture photometry, we find the centroid by balancing by moments. That is, you multiply the weight of the pixel, its pixel value, times its radial distance from the center. And from that, you can solve where is this balance point. Okay, that's what we're going to be doing here. So we're going to take the moment, divide it by the sum, and that'll give me my x centroid, my y centroid. And we're going to set the value of the function star centroid is true. If it's not true, we're going to jump out of the thing and say, ah, we failed. And if there was an error called, we're going to exit the function too. What the centroid is doing is it's telling us the coordinates of the light of the center of the light in the cluster of pixels that represented the star. So here we go. This is the center of the light. Okay. And it won't be a whole number of pixel. It'll be some kind of fraction. A good centroid routine will find the center of the light, even in a mess like this, to better than 1/10 of a pixel. So we're going back to this routine and saying, well, where are we now? Because we're distrustful, we're going to run the centroid routine a second time to make sure that we got it right the first time. Okay, and we're going, if that works, if the centroid was okay, then we're going to go and we're going to now try to do photometry. So this is what a routine called soft aperture photometry does. The reason I call it soft is we're using an algorithm that uses partial pixels to try to find out where the edge is. If you think about that, the star image is not smooth and continuous as we would like to think. Okay, see, it's all broken into, it's a cluster of pixels. So there's going to be pixels at the edge which have starlight in them, which can be either in or out. Okay, there's a paper in Monthly Notices of the Royal Astronomical Society back in 1998 that I picked up and used for this. And when we define this function, these are the values that are going in. We're going to put all these values back out again. This is the way we wrote this particular code. So here we are again. Okay, here's our first and last, and we're ready to scan this. And for this talk, I've used the much better quality image rather than the ratty looking one. So once again, we don't know where that centroid came from. We don't know there's really a star there. So the first thing we do is we define the region we're going to be looking. We set the value of the function to true because we hope it's going to be true, and we make sure that it's inside the image. Now, in our test, remember, we have said, well, okay, we're going to look at this pixel and we're going to say, is it inside this limit or is it outside this limit, or is it on the fence? Well, it's going to have to make a decision. So when we look at pixels that are out here in the annulus, we're going to have to make a choice. We're going to end up with jaggy edges. We're going to end up with pixelated edges. And we don't want to do that here in the aperture. We want to be able to say, well, if it's inside here, we'll count the whole thing. And if it's outside here, we're going to not count it at all. And if it's here, we're going to count part of it. So here's where that happens. We define some radii, the inside an aperture radius. And then here's where that happens. If it's entirely inside, it gets a weight of 1. If it's entirely outside, it gets a weight of 0. If it's in between, it gets an interpolated value. And then we're going to add to star sum, we're going to add the weight times that pixel value. And we're going to add an amount of a pixel plus its weight. So you can have a pixel that counts 50%. You can have a pixel that counts 10%, depending on its radial distance from the center. Okay, and then this similar routine and what we're doing here, we're not going to bother with getting nice tidy edges because we typically have 200 to 500 pixels in that outside. We can afford to lose one or two inside or outside. So we're summing them up, and we're going to put these not into a sum, but we're going to put them into an array. Okay, so we have an array called annulus, and its index is sky pixels. We determine it from counting how many star pixels we're going to have, and we're counting the number that go into that. Now, here's the graphic that shows what we're talking about. So here we have the soft aperture, and I colored these in by hand, which was really tedious. But you can see we have basically, it follows quite well. And I hope you can see it that we have jaggies here, right? Jaggy, jaggy, jaggy. Okay. We don't have to worry. We could do that. I mean, you know, but it really isn't going to give us a better result. Whereas here, it's going to make a big difference. Now you say, well, that's big enough, you know, a few pixels inside and out. It actually probably is not necessary with a radius of 6, which is the value used in these tests, or 5 rather, its value is. But if you have really small star images, really tight star images, as we did actually when we were early in the days of testing AAVSO net, we were using very sharp little refractors. We're using radii of 2 and 3 pixels, and it really made a difference as to what was included. Now, there's one more thing that's going to happen here. We got background star images here. This one you can see pretty well. If I crank out, and this one is just beginning to impinge here. How do we deal with these extra stars? Okay, they can, in this case, they don't, but sometimes they add a lot of value to the average sky brightness. And what we're going to do is we're going to sort the array of pixels, and then we're going to throw away the brightest 20% and the dimmest 20%. Okay, now there's been over the years a lot of argument as to how you do this. People take the median, they take the mean, they take various statistical measures. This one, we're simply throwing away 20%, the brightest 20%, and in order to balance that, we throw off the bottom 20%. You know, you can put a lot of effort into trying to improve this, and you probably, really the best answer is don't work with stars that have significant other stars near them. Okay, if you can't avoid that, we're taking something that is pretty effective at getting rid of that extra starlight. And then, as we did before, as we exit this routine, if there if we didn't find any star pixels, and if we didn't find any sky pixels, then the soft aperture photometry is 0, and get out of this function and return a value false. It didn't work. Okay, having done this though, when we get a value of true for this function, we now have all the information we need to compute the total light in the star, that is the star plus the sky, the average sky background minus impinging stars, subtract the average background from the light in the aperture, okay, compute the instrumental magnitude of the starlight, and assess the errors in these determinations. We've got all these values that come out of here. And so now we're going to call a couple, okay, if photometry is okay. So we've gone through this routine, we checked, we did a quick check on, can we get a good centroid? Yes. Can we get another good centroid? Yes. Can we do photometry and get it okay? And if that's okay, okay, now compute the magnitude. Okay. And routines like this, they really hate it when you pass zeros and stuff into them because they crash. So here's the magnitude equation. I'm not going to go into this a whole lot. I hope if you're doing photometry, you understand how magnitudes are computed. Okay, here's the magnitude minus log base. Oh, there should be a minus 2.5. Oh, That's a bug in the presentation. So it's minus 2.5 log base 10, the signal in photons, plus an arbitrary constant z. Okay, z is the fudge factor because it allows us to go from photons to magnitudes, and z will typically end up being a value like 22 magnitudes. So in other words, you just run this equation as it looks, you'll end up with a -8 magnitude star, which is not. So you're going to add, you're going to add 22, and so you're going to come out with a reasonable magnitude, like, oh, it's a 13th magnitude star. And in the single star photometry, it's important to assess z carefully. You do that by clicking on a star, setting the value of z to give you the right result. Then when you click on other stars, you get the right result. So z is your scaling factor. It's your fudge factor. And okay, carefully to note, I will change this. It's minus 2.5 log 10. That's just the definition of what a magnitude is. Okay, so here's the soft aperture magnitude. We're doing the calculation. It's basically doing just, see, and we actually have 2.5 log 10. It's there. And we normalize this by the integration time. And then we're also going to compute the noise. Now this, I won't get into the equations for doing this. They're in the Handbook of Astronomical Image Processing. You'll find a professional reference in Steve Howell's book, The Handbook of CCD Astronomy, Cambridge University Press. Everybody is using this. It's called the CCD equation. Okay, so we calculate these values. So on the single star photometry tool, then, okay, here's where the settings, here's your radii, 5, 8, and 15, which I've been using. My integration time, which is important. The single star photometry tool is a relatively dumb tool. So you have to manually set the integration time. You also are setting the gain, which is the number of electrons per ADU. Remember, ADUs are the pixel values, the readout noise, because these are all making the dark current, and finally the 0 point. So these are key values you're going to set. Then the result, what you get out of this thing is it gives you all the values that it computed. Okay, so this is your complete readout of the analysis. And then this is oops, another bug in the presentation. The front and the back of this is my settings. I should have had a result panel there. We'll fix that up, and we'll probably do something like, I'll at some point post a PDF file of the talk with the bugs corrected. There's always bugs in anything you do. Okay. Now we talked about the star profile a number of times. This is the software, or the code that produces the arrays that we're going to plot in the star profile. So we simply find the radial distance outward, and we produce two arrays. One is a radius array, and the other is the pixel value array. And we're going to plot those like this. And you've seen this a bunch of times already. Now there's one other thing that comes out, a very useful tool. And this is the curve of growth. Okay. Those of you who've been looking at this thing several times have said, well, wait a minute, he's hiding something from us. Now I'm going to tell you about that. The curve of growth is the curve that says, well, I'm going to, if I set the aperture to a different value, say I set the aperture to 4, what magnitude would I have gotten? Well, here's the magnitudes you would have gotten, and here they are. Okay, well, if you had the aperture set for 2.5, you can see you would have left out most of the light. You would have left out 4/10 of a magnitude too dim. If you'd set it for radius of 3, you would have had about 2/10 of a magnitude faint. If you set it for magnitude of 3.5, it would have been 1/10 of a magnitude too bright, and so forth. So here's value of 5. Okay, and then you'll notice if you keep making the aperture bigger, you're going to get more light. Okay, until you, and it just keeps on going up, and it typically does. But at some point, remember, every star has the same profile. Okay, which means that every star you do this to, the curve of growth should look the same for every star. It'll be noisy, they'll go up and down. Now, one of the things you can't see in this graph because they're too small is that there's a little red error bar. Now, the error bars are small at the smaller values, but as this gets bigger, you're now picking up more sky pixels, but you're not picking up much starlight. You can see the sky is not getting brighter, but the error bars start to grow. And what you do is you make a judgment call, really, that 5 is the value just before it's going asymptotic. Okay, you know, this will keep going up forever potentially. So you're going to pick this value. Now there's, in some of the other photometry tools in AIP for WIN, we also have a signal to noise ratio plot. And I don't have that in the single star photometry tool, but what you typically see is that signal noise ratio rises and then falls. So if you're doing more sophisticated photometry, you might tune for the highest signal noise ratio. Now, what's scary about that is the highest signal noise ratio typically appears at 70 or 80% of the value where it tends to go asymptotic. Most people, including me, I go for a slightly lower signal noise ratio in order to be assured that I'm going to always get all of the starlight. So that's basically what I have to say. This is the abstract written for it. And we've reached the end of the formal presentation. I hope I haven't run too far over time. And I think we're open for questions now. So there's Lauren. Okay.
Thank you so much, Mr. Berry. That was a fantastic talk. I really am kind of in awe at the amount of hard to find out information that was just shared. Before we move on to the questions, and we have quite a few here, I want to go ahead and make a small announcement because I did receive a question from, or a comment from someone in the audience who's brand new to photometry and said this is all very intimidating. So I want to make a point that what you just showed is a behind the scenes of software aimed at programmers, but it's not how you actually do the photometry when you just have an image and you're like, I'm going to go find out what magnitude this star is. That procedure is a lot simpler. So don't worry if you're a beginner in the audience. I'd recommend that you go back and look at our past webinars. Like we had one by Bob Buckheim on getting started with CCD photometry that showed how you would walk around in a software like Mr. Berry's and very simply perform the operation of getting your magnitudes.
For that person, let me go back to the very, very beginning, which is
Okay.
when I introduced it. It takes a while to get back there. Click, 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 click. Okay, remember I said, okay, you pick the tool. Mm-hmm. You have the tool comes up. And then here's the tool up. I've got the radio showing. And you take your mouse, you over and you click on the star and a number pops up. That's the outside view of what you do when you do photometry. Okay,
Right.
I mean, it's really fun. Okay, when
Mhm.
I was doing this thing with M67, I could go click, 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 click. I get a magnitude for each star. That's the video game part of astronomy, and you don't have to know how this stuff works. However, part of what I hoped you learned was that if you go and you click on this star, you're in trouble because it's sitting right next to that star. Um, so it really does, it really not normally that complicated.
Right.
This is the easy part. This is the
Mhm.
fun part.
Mhm. All right, thank you. So now moving on to some of the questions. Let's see. Let's take some of the non-programming ones first. So this one comes from Joe Fragola, who asks, if using an EV scope, how do you access the dark frame data in order to do your calibration? And also, I don't think that EV scopes can capture flats, just dark frames. Do you know anything about that?
They cannot capture flats, and it's very frustrating to me.
Mhm.
However, the optics are very, very simple. You have a paraboloid focusing um, on the sensor, and there's really nothing else in there. There's no diaphragms or anything that might cause vignetting. So yeah, flats are an issue. Okay, with the EV scope, what you do is you write to unistellar support. Okay, first of all, you'll notice that you can upload your images. Okay, so first thing you do is you go upload your images. And it's an automatic function, the EV scope software. Then you write to the support people and say, I just uploaded a bunch of images from EV scope, blah, 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 which has its serial number. And please send me a link to my images. 2 days later, you get back a link, which is like 200 characters long. It's got some,
Mhm.
and you download 5 GB of data, which will consist of typically 2,000 or 3,000 FITS images. And it's very nicely organized. You have the individual images, and for each time you did a live stack, they stack all those images together for you. So that's what I was using when I showed the 900-second exposures.
Hmm.
That was okay. This is one of their uh, uh, 900. Well, what was it? 250 some images averaged together to get that. I am told that they expect to make it so that you can automatically log on, give a password, and download your data, which will be much nicer than having to write to support. But I have to give support great credit. At this point, they know me. They go like, okay, here's your link. The biggest problem is you take your good data Thursday night. By the time the link gets to them, it's Friday evening,
Mhm.
and they take the weekend off, so they don't get to send you your
Mm.
link until Monday. That's why I say it takes 2 days to get your data back typically.
Mhm.
But I would like to see, I think they will automate that at some point. And you'll be able to get your data back.
That would be great. Okay. The next question here comes from Guy Stringfellow, who says, hello, and thank you very much for the presentation. Can you please explain exactly what encompasses stacking images compared to, for example, median combining a set of images?
And this, I think well, stacking is simply adding them together or taking an
Mhm.
average. And either way works. You can add them or you can take an average. If you are working with integer software, you add them. If you're working with software that uses floating point data, you would average them so that you'd have partial pixels, or you wouldn't have You wouldn't have integer values, you'd have floating point values.
Mhm.
AIP for Windows averages, although there's actually an option to add them. Um, um, you can use the other routines that he mentioned. Compare the pixel in each successive image with the images. Say you have 100 images, okay? For any given pixel, you've got 100 different values. In theory, they should be the same, okay? But a satellite and airplane went through, so 2 of those values are just wildly big. Okay, if you use a median, you simply exclude those extreme values. If you use k-sigma, what you do is you compute the median value and then you throw away the ends, which are contaminated by passing airplanes and satellites and Starlinks.
Right. Okay, thank you. And next question here, while we're on the topic of stacking, Jeff Myers asked if there's any reason to measure 10 1-minute frames separately versus averaging them together and then analyzing the final stack.
My preference is actually to measure the 10 of them and average and not only average, but also compute the standard deviation of the result. Because when you just stack the images together and get a magnitude, you don't know how good that magnitude is. But if you measure the individual ones and you compute the standard deviation, then you can say, the magnitude I get is, for 11.25 plus or minus 0.003. Well, that would be awfully good. 0.03, realistically, about 3% error. And with ordinary photometry, you're typically looking at a 2% error, actually not error, uncertainty in the magnitude. And I believe AAVSO basically would like you not to stack the images. But when you get down to really, really faint stars, you're starting to deal with, can you get a good centroid and stuff like that? So stack them will give you a better centroid, but it makes it harder to assess whether or not the photometry is good. You simply have a magnitude with no real sense of how good that value is.
Right.
And as an exercise for yourself, do it both ways. And then compare. Okay, the average magnitude by averaging the 10 and the magnitude of the stack should be the same. And of course they won't be. They'll be slightly different.
That does sound like a good experiment.
Always be willing to do experiments. People, for instance, will ask things like, well, the images of my telescope are a little bit soft on one side and it's a tiny bit of coma because it's a Newtonian. How does that affect my photometry? And my answer is, don't go on the cloudy nights and ask someone for an expert opinion. Pick something like M67 and take a picture with a group of stars you've selected in the upper left, in the middle, in the upper right, boom, 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 and then do the photometry on them and find out if there's no problems with vignetting and stuff. You should get the same result wherever the star is in the field. And if it doesn't, now you know that you've got to pay more attention to your flat fielding or something like that. To get that problem out. And again, the assumption here, and the assumption we try to make, is that the profile of the star will be the same everywhere in the image. Reality differs slightly. For good photometry, you really don't want to have your your program star in the center of the field and your comp stars off on the extreme edges.
Mhm. Right. Okay. The next question here comes from Michael Gardner, who asks, can I do useful photometry in an urban environment?
Oh yeah. Stars in bright city lights and stuff like that affect stars very, very little compared to how they affect nebulae and galaxies and stuff like that. So, I mean, I live near a small town. I have about a Bortle 5 sky, and I'm reaching 16th magnitude with a small scope. So you can easily do decent photometry, 12th, 13th, 14th, 15th magnitude. Well, maybe not 15th, but 12th, 13th, 14th magnitude in a bright sky with no trouble. And if you have a big scope, again, the magnitude scale just goes lower. And you've seen from the images that I showed, the we're going to subtract off the sky background. That's part of what we do. Okay, we make it go away. The sky background adds noise. Okay, because of that random fluctuation in the signal. But if you can see something, you can get photometry off of it.
Great, thank you. Okay, next question here from George Smith, who asks, are professional cameras significantly better?
Of course they are. um, I'm not sure quite what you mean by professional. If you're talking about astronomical CCD cameras, if possible, you're looking for, well, okay, it's going to be a choice of the chip quality, whether or not the chip has more hot pixels or less hot pixels. In a professional camera, they would probably be using the Class A chips or something like that, the chips that have no defective columns, fewer hot pixels, and so forth. The quality of the amplifier and whether they break the signal into 12 or 14 or 16 bits. But well, if you buy a camera today, your camera is so much better than a camera you would have bought 20 years ago that you're going to be able to do good photometry with no problem, because even a cheap CMOS camera, if you use it well, if you stay within the limits of what it does well, you're going to get good results.
Yeah, that's so true.
I mean, the key things are, don't saturate. The EV scope, for instance, really can't do good photometry brighter than 11th magnitude because the stars are saturated. And below 15th magnitude, it starts to run into, the results are just too noisy. If you push it with a 15-minute exposure, you can do 16th magnitude stars. But in a 4-second exposure, you're probably limited to about 14th.
Okay, thank you. So just one or two more questions on the topic of general photometry, and then we're going to get to the ones about programming. But real quick, here's one from Wayne Clark, who asks, can you do accurate photometry with elongated star images?
You can actually, and that is because the profile of every star in an image is the same, or at least, very close to the same. This would go back years and years and years. When we were writing our first code in BASIC, I think, I got in touch with Phil Sullivan, and he sent me a bunch of images. And that would have been the old days when you would have mailed a floppy disk in a mailer to another person, of photometry of some star. And his mount wasn't tracking well, and the stars were severely chromatic and they were trailed. Okay, so here's Phil's images, and the star goes like boop, 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 boop. And then he resets the mount, and it goes boop, 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 boop. So it's trailing along like crazy. And I think it was an eclipsing star. Okay, so you're going to get a light curve that goes up. I ran the photometry on it, tried a bunch of stuff, and I was amazed. These horrible star images, the centroid routine is really good at finding the center of light of the star image. Okay, and remember, it's a comparison. Okay, you're going to be a comp star and your variable. Okay, and they're going to be affected equally by the trailing. And so what came out was a very nice eclipse. And I went like, wow, I wouldn't have thought it would work so well. And that plot actually shows up in Handbook of Astronomical Image Processing. Now, I would not recommend you use trailed images, but if that's what you got and you can't improve it, remember the other thing people do is they say, well, I tried to get my focus absolutely perfect. Well, if you think about getting your focus absolutely perfect, that means you're putting as much light into the smallest thing you can, and you're likely to be getting saturated pixels in the centers of brighter stars. So a lot of photometry with small telescopes is done with the telescope slightly out of focus, because then the star image, like this one on the screen, covers more pixels, and you don't have a saturated core. You have a kind of a flat top thing. And with DSLRs, it's commonly recommended to be slightly out of focus. Because the pixel grid, instead of being pixels of equal sensitivity, is red, green, blue matrix. And so you want to make sure that you have the red, green, and blue matrices equally sampled.
Okay, thank you. And you actually just touched on one of our next questions, which was about how AIP for WIN handles defocused stars. Is it just the same way as in focus?
Same way, yeah. The centroid routine actually works very, very nicely on planet images too. There's AIP has a planet stacking algorithm, and it just uses a gigantic aperture, 300 pixels in diameter, and it centers an image of Mars or something like that to the nearest tenth of a pixel. I mean, what's amazing is you can centroid it and then centroid it again, you keep getting the same result. And in a series of like 200 images, or boom, 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 you then make a movie out of it, and Mars does not go like this. Mars just sits there and jiggles a tiny bit.
That's great. Okay, thank you. And while we're on the topic of pixels and how they're handled, Sidhu asked, how does the pixel size affect the end result?
You want enough you want enough pixels in your star image that you're not getting down to using a really, really tiny aperture. Because then you start to get into that business of square edges, and is any particular pixel included or not. I'm not sure exactly what is behind the question. If he's thinking, okay, well, let's put it this way. In the olden days, all cameras had 9-micron pixels, excepting professional cameras, which had 25-micron pixels, or 15-micron pixels, or 12-micron pixels, or 9-micron pixels. We typically, nowadays, we're dealing with 3.75-micron pixels, and we're rapidly moving into an era of 2.5-micron pixels. The key is, are you sampling the star images adequately? These images are very well sampled. We got lots and lots of pixels. There's like 100 and some pixels in this little box. Again, if the brightest pixel value in the image is greater than typically like 70 or 80% of the peak value, you're running a risk of saturating that pixel. When the pixel saturates, you lose light from the total image. And that's what happens with the EV scope on bright stars. It keeps on recording them because you're looking at the light from the outer edges, but this few pixels in the center will be greater than 65,000, and you'll be losing light out of those. And when you actually plot that, I actually did a plot. Let's see if we can get all the way back to the back end here. Doesn't go real fast, does it? I had a couple of extra things here. Okay, here is a plot for M67, which I did using the single pixel tool. Okay, and this is the V magnitude, the official standard V magnitude, and this is the raw instrumental magnitude from the EV scope. And you can see, like, oh, these follow up so beautifully. And then the curve necks over, and because you're losing light now from the EV scope, and so it's producing values that are a little low. Now you say, well, wait a minute, what are all these guys? This is M67 is so crowded that you often will get light from an adjacent star as you get fainter, jumping into it, and so the raw instrumental magnitude will be too bright. You'll notice it never happens the other way. It's always this way. So, I mean, with apologies to visual observers, I tried visual observing, and I never could convince myself that when I looked at a star that I could say that is 12.3. I'd look at it and say, that's 12-ish. Okay, I look at this and say, without even, very, very, you can't do worse than 1/10 of a magnitude with photometry. Although people do manage to, but if you're careful, you should be able to, somebody with a good system should be doing 10 millimag or better on stars that are not crowded together typically. And I know 2 or 3 would be 2 or 3 2 or 3 hundredths of a magnitude, 20 or 30 millimags would be pretty typical.
That's great. Okay, we have one more question before we get to the programming questions, and this one comes from Paul Norris, who asks, will the results of your photometry be different depending on whether you use FITS format images or JPEG images?
Yes, because JPEG is a lossy compression routine. JPEG images are carefully designed to look good to the human eye. Okay, but they throw away data because it's obvious they throw away data because your image is a tenth as big as a TIFF image of the same size. If you can't avoid using JPEG, then fine, but it's best not to. On on the other hand, I like to play and experiment. And I mean, one of the things I'd like to do here would be to take my color image that came out of the AAVScope and do the same kind of photometry on that. Now that data has been very non-linearly scaled, okay, because it's been designed to, well, it's been processed to look pretty to the human eye. So it would probably be a horrible curve that do something like this and be scattered all over the place. FITS images by design give you back what the sensor saw. JPEG images give you back what is small and easy to email.
Yeah. Okay, thank you. Now, going back over here to some of the questions about AIP4Win and programming. Okay, first of all, we have had a couple questions about what programming language are you using?
The program was written in Visual Basic 6, okay. Which was the last version of Visual Basic that was not fully OOP, okay, object-oriented. It was kind of a mix of somewhat object-oriented, somewhat procedural. It was designed by Microsoft to be very easy to prototype software. It dates back to about 1995, 1996. Its problem nowadays is that it's 32-bit code, which means that the program can access about 2 gigabytes of data. Now, by the time its runtime libraries and stuff are loaded, VB6 can access only about 1.3 gigabytes of memory. And we use 32-bit floating point data throughout. Okay, so when you have a color image, we have 96 bytes per pixel. Is that right? Yeah. No. Yeah. And you have a 10 megapixel image. You can suddenly see you're using a good fraction of the memory that's available to you. So AIP4Win can work very nicely with 6 megapixel DSLR images. Somewhere around 8 to 10 megapixels, you start to have to be very careful how you use your, anytime if you have 3 images up on the screen, you're fine. Add the 4th image and you run out of memory. So on the other hand, just the other day I loaded a monochrome image, okay, which takes this much from a QHY 600 camera, which is a 61 megapixels. So it only takes 180 megs in memory. That's easy because we got 1.3 gigs. So I can do almost anything I want with these huge 65 or 61 megapixel images from the QHY, but a much smaller color image from a DSLR will leave me with too little memory to work with.
I see. Okay. On that topic, Wayne Clark had a question. He said when Wilman Bell was in business, there was a list of DSLR cameras that would work with AIP for Win. Is that list still available? Because his DSLR wasn't on the list. I'd like to see the list.
No, when Wilman Bell went down, they went down really quickly because of health issues that Perry and Pat Ramaclis, who were the owners, had. And I don't know exactly what happened, but I was not able to get access to some of that stuff. And in September 2020, we lost our house in the Beachy Creek wildfire in Oregon, which is why which is why the version of AIP for Win is 2.4.10, because I lost the code to 2.4.8, which was a very, very stable beta that had been running forever. That computer was burned up. I had another computer, a newer one, that had all the subsequent development work that I'd done. And so the lowest value I had a good backup for was 2.4.10. So I stripped out the registration code, and that's what we put up on the Groups.io website.
Thank you for doing that.
It's one of those things, we came, that far from losing the source code entirely.
Wow.
Now, to develop, when I realized that the software would have no support unless we did something about it, I called up my buddy Jim Burnell, who was the co-author of the book and worked with me for years on the software. And he had an old Windows 7 machine that he was using to make the distribution packages. So he shipped that to me by FedEx. And I set it up, and that's how we built the distribution for the new code. And 2.4.10 had in it a bunch of diagnostic code for me as a programmer. So everybody who runs this thing, they run into these things where you get these development messages. And I did not have time to find them all. So there's some residual bugs in the software that's available to people. And what the Groups.io people do, which is, I totally appreciate the community there. They will answer a lot of questions that come in from new users. And I'm, dealing right now with a question that's up on the site of a guy who has installed it and it's running just fine on his computer, but he has a couple of students and it won't run properly on their computers. I wrote him and I said, I think what's going on is they have school computers, and there's software on the school computers that says if something doesn't say Microsoft, you can't run it, or something like that. So every time you have to diagnose a problem in an individual's computer, you're dealing with a computer that's like no computer I own. Because and by the way, I've just installed AIP for Windows on Windows 11, and it runs just fine. And
Good.
And allegedly, Windows 11 fixes a lot of problems that Windows 10 had.
Okay. Hopefully, probably my computer's going to update without my will one night and I'll find out then.
No, you can tell it not to.
Mhm. So, oh, where did the next question go? I've got quite a queue here. Um, okay. Oh, yes. So on the topic of development of AIP for Win, we had a couple of related questions. One was, will the existing AIP for Win bugs be corrected in sometime in the near future? And the other was, more generally, what is the future of AIP for Win look like right now?
Um, what I want the future of AIP for Win to be is to move into a different programming platform.
Mhm.
Um, and that supports 64-bit code. Okay, then the limitations will go away. I see absolutely no sense in playing around with code that makes pretty pictures anymore. There's already lots of other expensive ware out there for handling DSLR pictures. And it's getting, I mean, even Photoshop and some of the other software out there is doing a great job with pretty pictures. So I intend to focus on science applications. And we are looking at, greatly improving its handling of astrometry. In the Visual Basic 6 routine, my last working version was 2.4.50. Okay, so I had done a long time past where we had gotten to with 10. Okay, but 10 is completely compatible with 8. So if you have a working version of 2.4.8 and you simply take the executable 2.4.8, you can have the two executables can sit side by side in the same directory, and Windows doesn't know which one of them is running. So you can fake out Windows. The major difference between the two things was that 8 requires registration, 10 does not. And that, well, I keep saying no registration required, but you pay a price. The number of complaints of stuff that doesn't work have actually been amazingly small. Mostly you have to put up with Windows that every time you save an image, it says, it just goes through a bunch of checks that I put in to make sure I was saving properly, for example.
Right. Okay. Next question here. About when you were showing the procedure where it was calculating the magnitude and just displaying it, you were showing how simple it can be and video game like. We had a question come in then that said, wow, so the target star magnitude is computed without needing to select a comparison star?
Okay. Yes and no. Okay. There are 6, I think it's 6, photometry tools in AIP for Win. What I was showing you was the single star photometry tool. Okay. When we wrote the software and we wrote the book, we were thinking of educators a lot. Okay, and a single star photometry tool is nice because you can go into an image like the one of M67 and you can click on different stars and you get magnitudes. But then you have to realize you have to set that 0 point. So you go to something like M67 and you have the list of the magnitudes of all the stars, and you click on a star with a known magnitude, and then you go into the settings tab, which would be here, and you set the value of Z to be a value that gives you back the catalog value. Now you go click on other stars, and bingo, they give you back the catalog values with small uncertainties. Okay, now this was to show you, in terms of an educational thing, it showed you that a raw instrumental magnitude is a magnitude that is unanchored because Z is something that you choose. Okay, the next is the single image photometry tool. Okay, and here it expects you to click on 3 stars. It expects you to go over and you click on the variable, and this will then turn up, it will say yes. Click on your comp star, and it will click on the comp star and it'll put a C next to it. Then click on your check star and it'll put a K next to it. And then you enter the standard, then you enter the comp star's magnitude. Okay, so it's a 11.25 magnitude. You put this number in. When you click, as soon as you finish that, it will give you back, okay, the star minus magnitude, star minus sky and instrumental magnitude. So there's your magnitude. And then it will give you the measured magnitude. And now it's making a comparison between the comp and the variable. And it will also tell you what the computed magnitude for your check star is. So you should get, when you click on that, those 3 stars, you'll get back the magnitude of the unknown magnitude, and you also get back the magnitude of the check. Okay, and then visually you go like, okay, the check star matches the book value. I'm okay. And this is, again, thought of as a teaching tool. Okay, so you can have students and they can go through and they can begin to understand that all magnitude calculations are differential between a known comp and an unknown. And then you've got to check, because who knows that the standard, that your comp star might be a variable itself. Okay, right. So it's intended for teaching.
Great.
The multi-image photometry tool does almost exactly the same thing as the single image photometry tool. It expects you to pick 3 stars, but you can put in a list of like 500 stars, and you select on the first one, and you click, 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 here's the stars I want, and then you click do it, and it loads each one of those 500 images and runs the photometry on them. Bang, 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 bang. And it's really cool because it'd be going like 2 or 3 images a second.
That's
If you
great.
think about doing that manually, you'd basically be dead by the time it was done.
Right.
Okay. And when and it's now, I consider it out of date. However, it works really well, and we have observers who've been using it for years. And to keep their results consistent, they keep using it so that there's no changes in their techniques. Okay, so that's internal consistency of your work. Yeah, and it does nice things like it computes the Julian date and stuff like that. So it's producing a much more valuable output. The next tool is the one that I want people to use because it is the most sophisticated. And this is designed for production photometry. So I can fill in, for instance, my observer value, my latitude, my longitude, all the values that I need to produce a complete report. and AAVSO report is one of the formats. Center for Backyard Astrophysics is another format. And there's also a dump every bit of data you ever get format. But so my observer, I set my observer and it loads my observer thing. I can recall that. I can save that. And I can also recall my observer format for my old house, where the BYY was the same, but it was in a different location. Okay. Or if somebody sends me some files to look at, I can load in that observer's stuff. Then there's
Right.
the instrument thing, which lets me put in the telescope data. Then I can make a list of the images. Then I pick my aperture. Then I can pick up all the stuff for a star. Like, I can have dozens and dozens of little star files, and they will fill in all the data I need for the check and multiple comps. And then I can do different. And then finally, we have the execute thing, which also has a star that you're now dealing with things like asteroids that are moving through the field of view, but you have to keep the stuff, it's designed for heavy duty production stuff. And then finally, there's the magnitude extraction tool, which is designed to find every photometric star in the image. And I've done some stuff with globular clusters where I've gotten 8,000 stars out of the red, green, and blue images. And then you can plot an HR diagram.
Whoa, that sounds really cool.
So, I mean, as years went by, we developed these different tools to do different jobs. And the magnitude extraction tool, after spending like 3 days manually doing M67, okay, with a single star, I went into the magnitude extraction tool, and like in 3 seconds, it did all the stars.
Wow. That's
So,
wonderful. Okay, I'm definitely going to be looking into that. Next question here comes from Ari Sequiria, who asked if there is an updated tutorial available for AIP for Windows. Ari says that they have the book, the original CDs, and version 2.4.10 running okay, but Appendix C tutorial does not always seem to match up with the actual software.
no, it doesn't. As a programmer and a book author and stuff, I have to say that programming is very fast compared to documenting. Okay, and keeping a book, which gets printed every 2 or 3 years, and keeping software, which you can go through. In the earlier days of AIP for Windows, I tried to release a new update every 2 or 3 months, because we kept getting user requests, and we kept getting bug fixes, and so we just kept the software moving forward. After my partner in crime, Jim Burnell, got a promotion at work and suddenly got more pay and more work and less time in his life, I didn't have enough time to keep up all of the stuff that should have been done. And then, of course, after your house burns down, you don't have you're doing things like we're buying chairs and beds and realizing you don't own any books anymore at all.
Oh man.
So yeah, you don't want to do this in your life. If you want to simplify your life, burning down your house does not do it.
Oh gosh.
But as you can see, I now have a nice office, and over there in the corner is my EV scope. which for quite some time was the only telescope I had because all my other ones burned up.
Oh no. Gosh, I can't even imagine.
Um, you get to do some interesting things with the insurance company because you have to list everything that burned up.
Oh wow.
Yeah, yeah. What do you do? Uh, the the I had some interesting negotiations with the people because the insurance people because I said, well, I had about 4 huge library style bookcases covered with books, and they were most of them are big academic books.
Mhm.
And this is the kind of book that costs between $60 and $120 book. $120. And we agreed to make it simple to compute that um, we would we would put a value of like $500 on each shelf foot of books. And then we
Wow.
just calculated shelf feet. So I didn't have to give all the titles. But yeah, it's crazy.
Yeah, for sure. Wow. Okay. So our next question, actually, we have 2 questions here, which are related to something you were talking about earlier, the 0 point. First, we had a question asking if you could say why is the 0 point in the magnitude equation uh, important, and the other question asked if you don't set the 0 point, then does AIP for wind just use a fixed 0 point for each frame?
It uses a default value of 25, I think.
Okay.
And 25 for back when we wrote the software, 25 gave you something that was typically within a magnitude or so of the right answer. It's very important to understand that magnitudes magnitudes are always comparisons between a standard in the sky and your unknown. Okay, and all we do, all zero, all the value, all that Z is doing is taking that value and cranking it down to something which is realistic.
Mhm.
Now, as they've developed the science, um, there's a number of different ways of doing magnitudes. And if you want to get really confused, you can Google how are magnitudes determined, and then look for the university level lecture
Mhm.
series. You'll find PowerPoints out there describing Vega mags and AB mags and different magnitude systems. And they're all based on a standard or group of standards. Um, in the AAVSO universe, we use magnitudes in the Landau system, where Arlo Landau, who passed away recently, determined, not sure how many there are, there's something like 60 standard fields located around the celestial equator. Each one of these things has a bunch of stars. Those stars were very carefully and meticulously standardized against the master list of 10 stars that were used to standardize the Johnson Cousins UBV system. Okay, it was originally the Johnson system, Johnson Murray, and then it was expanded to Johnson Cousins, and they added the R and the I filters.
Mhm.
So the Landau fields are your primary, well, they're actually secondary standards, but people use them as the primary standards. So if you want to calibrate your system, you go and you do photometry on Landau fields,
Mhm.
and you get to, and then we have things like M67. Let me, oops, yeah, here's, okay, and this is a standard chart. M67, I hope it's big enough for people to see, but a lot of stars, and there's a visual magnitude or a star number for each one of those. And then there's a list of, there's about 250 stars there, and you can get UBVRI magnitudes for every one of those stars. Those have been meticulously done. And that's how I plotted this when I wanted to check.
Mhm.
So M67 is now, near the meridian at midnight now. So, shoot a picture of M67 or a bunch of pictures of M67, get the standard chart, and, start figuring out how photometry works with standards.
Mhm.
Now, what the chart team does at AAVSO is that they go to the field of your star you want a photometer, and they've standardized comp stars.
Mhm.
Okay, so your field will have comp stars in it that have been carefully standardized against Landau standards and standards like this. Okay, so your comp stars are basically an extension of the standard magnitude system. But there's a lot of work that goes into this from the chart teams and stuff like that. And then Arnie Hendon's APAS thing, where he photometered the entire sky. It was an AAVSO project, typically to about 20 millimags accuracy.
Mhm.
And APAS, I think the whole database is available online. I'm not sure, but basically you can get. Yeah, I think what you can do is on the AAVSO website, I can't give you a link, but you can ask for all the APAS stars within a given distance of any spot on the sky.
Oh, that's
And with a
great.
few tiny holes, it will give you back the magnitudes that their system has determined.
That's a great resource. Good to know. Thank you.
AAVSO website has many, many secrets hidden away in not the world's best interface. And
Yeah.
if you can find them, there is really good stuff there.
Yeah,
You
there
do
sure
have to
is.
search. The biggest problem I think with a website is you have to know what you're looking for
Mhm.
before you can search for it.
Yeah.
Okay, if you know what you're looking for, you can find it. If you don't know what you're looking for, you can't figure out what the keyword is.
Yeah. Yeah, we've been discussing better ways to structure it, but it's because there's so much good stuff on the website, it's going to have to be a big effort, you know?
It's a huge job,
Yeah.
and it is a very, very rich resource.
Yeah. Okay. Next question here. This one comes from actually multiple attendees have asked about this one. The basic question is, since there's been a change up in the availability of photometric filters and the new ones have slightly different spectral responses, do you know if the AAVSO has published any information about how suitable these filters are, and can we use these new filters for photometry?
Um, the answer is complicated. I've been involved with some of the discussion groups about this stuff. And basically, COVID slowed down and complicated everything with getting filters.
Mhm.
Um, the classic Bessel filters, which are made by dyed glass, um, are complicated and labor intensive. And I suspect, but I don't know it for a fact, that it became hard to get those types of glass from Corning and Schott. This is specialty stuff. Um, and I've made filters using this. You have to, the raw blanks that come from the companies that make them are not flat. Okay, so first you have to put them in a polishing machine and polish the surfaces flat. Then they have to be right. If you want a circular filter or a square filter, it has to be cut size, the edges. Then they have to put it in coating machine probably and get it clean. Then because they're round, you have to cut them out with abrasive, and then you have to assemble them into a little filter and glue them together and stuff. They, however, interference filters, which I mean, in the simple way, they put the substrate glass into a machine. A series of coatings are put onto it according to a formula, and then the interference filter has the right spectral shape. Again, that stuff was probably delayed, because everybody wants to buy narrowband filters, okay, for pretty picture photometry. And only a fairly small number of people are looking for filters for doing photometry. So, if you're a manufacturer and you have a choice between making something that a lot of people want and making something a few people want, you make the stuff that people, okay, but they are, the companies have become very, very serious now about picking up, now that the COVID era is looking like it's ramping down. And I know that at least one company, and probably many companies, are working on getting their formulas made so that the passband shape of the interference filters matches the classic dyed glass filter profiles. And the reason is not that you don't get good photometry. Okay, with the argument is that it's, let's put it this way, it's the people that make these filters are very good at making what are called bandpass filters. That is, they transmit nothing, then the filter comes on, they transmit as close to 100%, then they're flat topped and they come back down again. So you have a transmission band which is sharply defined. And for almost every technical purpose, this is what people who buy filters want, excepting astronomers. And astronomers want, in order to maximize the value of 75 years of photometry done with dyed glass filters, which have these sloppy band passes, they can make them, but you have to, it's only now that they're beginning to realize that it's critical that the photometry we do now matches the photometry that's been done for the last 75 years. So we're in a transition period. I expect okay, the other thing is that photometry done with the square filters can be transformed into the standard system, but it's an extra step. Okay, now ideally, okay, because the bandpass is right, it's centered on the right thing, and but its shape is different. And for a nice ordinary sun type star, you're going to get the same result basically with the dyed glass V filter and the square bandpass V filter. If the star is really, really red, okay, and remember B minus V for red stars, that became multiple magnitudes, then this sloppy bandpass is going to pick up extra red light at this end, and your star is going to come out too bright. Okay, but if you know the color of the star, you can then transform by applying a small correction that takes that extra bit out. And that's what transformation does. It takes the raw results you get with your instrumental filters and force fits it back to being the standard things. And again, what you do then is you take your filters and you do photometry on an object like M67. And then you run this through the right math and it says, oh, well, this star comes out your your BVR magnitudes can be crunched over by applying this math to them to produce a standard BVR filter.
Right.
There should probably be a webinar on doing transformation if there hasn't been already.
I have some great news.
Yeah.
Yes, we've actually just scheduled a webinar all about doing transformations. That one will be the June how-to hour. And Tom Calderwood will be the presenter for that one.
Oh, very good. I know Tom, he's another Oregonian. The standardization is the key. Right now, something like 10% of the people submitting photometry are not doing transforms. Because, you have to spend a couple nights figuring out the transform coefficients. You think, well, wait a minute, I only get so many clear nights. I just want to shoot my stars and send in my results untransformed. So Tom, I think will probably make an excellent plea to learn how to do transformations and do them, because then your filter types become much less critical, because whatever filter you're starting with, you should be able to produce standardized results. So it'll be less, but I think the message is good new matching filters are in the pipeline. And I think Arnie Hendon has filters right now, which he is testing to verify that they work correctly.
Great. Okay, so we still have probably about a dozen open questions, but we are now at the 2-hour mark. I want to give you an option on whether you want to try and answer a couple of the last questions, or if you want to go ahead and start winding things down.
Real quick, what kind of questions are they?
We have another question about filters, one about the 245 cookbook camera, one about the difference between CCD cameras or CMOS cameras, one about the EV scope, one about Astro Image J. So it's kind of all over the map here. There's like two on AAP
why don't I'm going to stop sharing because it doesn't sound like any of those need sharing. Why don't we try to get pretty quick answers for them?
All right, blitz round then.
Yeah, we'll just sort of whip through them and see if we can't.
Okay, so one quick comment here was submitted by Mark Botteroff, who he had a reference for a paper on transformations from Johnson magnitudes to Sloan magnitudes. In case you have those Sloan filters, I'm going to copy his comment over to the chat. And all right, next question. Let's go to how about George Smith's question on how accurate in terms of percentage of intensity can you measure a star's brightness with amateur quality cameras? He gave an example of a 10th magnitude star with an 8-inch f10 scope and 1 minute exposure.
You should be able to get about 5 millimags under good conditions. It, 8-inch scope is a quite decent sized scope. A 10th magnitude star is in today's universe a really bright star. Yeah, you should be able to do at that level, let's put it this way, when you look it up on the photometry table, you'll probably find that the comp stars give a magnitude of like 10.500 plus or minus 20 millimags. Okay, you may be able to get a differential magnitude that's good to 5 millimags, but your result is going to be constrained by the fact that your comp stars are not known well. Now,
Makes
the
sense.
AAVSO reporting format, when you report that 9-character star number, if we get more accurate values for that, your data submission can be recomputed to be as accurate as the new comp star magnitude is known.
Okay, thank you.
They were thinking ahead when they did that.
Yeah. All right, next question here. Does AIP for wind take the average or the median of the background pixels when it's sampling using the outer annulus? And if it does take the average, does it perform any outlier tests on the pixels from that outer annulus?
It does not perform a test. What it does, it takes the average, but then it discards, it basically takes what I call the mean of the median half. In other words, we take the middle 60% of the stars and we average them. So you might have missed it but what the software does is sorts them from bright to dim, then throws away the brightest, throws away the dimmest, and averages the middle one. So it's basically does the same thing as a K-sigma or a median, but it's actually more violent because it throws away the top 20%. So if you have a star impinging on your star that fills more than 20% of that radius, you'll begin to get parasitic light. But it's actually very efficient in getting rid of parasitic light from nearby stars.
Great, good to know. Next question is about, is there a quantitative criteria for deciding how big your photometry annuli should be, the radius for the star and the sky background?
If you use the profile tool and you can set it, you want to set it so that the star is almost going level, but not quite. Because your highest signal noise ratio will occur when you're cutting off about 20% of the star's light.
Interesting.
If you go strictly by the highest signal noise ratio, it will make you nervous because you're cutting off a bunch of light and you're going like, can I really get away with this? The answer is yes, you can, but it makes me nervous.
Right. Okay, thank you. Next question, if your camera's gain is 16 electrons per ADU, but your camera is a 12-bit, your software is saving the image as 16-bit, do you need to divide the gain at 12 bits by 16, so that's the conversion from 12-bit to 16-bit, and then just set the input parameter gain at 1 electron per ADU?
I think that's true. Yes.
Okay.
Okay. Handling questions like this verbally.
I know.
No,
it's in the Q&A
but
box.
I think he's right.
Okay. Okay. Thank you. Is there some sort of set procedure? I assume the numbers 16 and 12 aren't too special there. What's the goal of that conversion there?
Oh, well, the gain is simply the number of electrons in each ADU. When the camera is actually taking 12-bit data, but then you just multiply everything by 16 to make it into 16-bit data. You've diluted that by a factor of 16, and then the number of electrons per ADU would drop.
Uh-oh. Can you still hear me, Mr. Barry? You froze up.
Oh, I'm sorry.
Oh, now you're back. Great.
Okay. Oh, it says my internet connection is unstable.
Okay. Well, all the more reason for a blitz round, I guess.
Okay. So just be, if you, As long as you got it, I think what he said is correct. I think it's 1 electron per ADU.
Okay. And I understand more now because of what you said about why you're doing that division. Because you're trying to get back to the 180 mark. Okay, so next question here. Oh, this one's a little bit ironic, and I'll say why in just a moment. Ron DiUlio has asked if you can comment on Astro Image J and its photometric applications for photometry of exoplanets specifically. And before you answer that one, I'm going to say the reason I said it was ironic is because it appears directly above a question from Dennis Conti, who is our resident expert on using Astro Image J for exoplanet photometry. And he did have a webinar on that last year. So Ron, I would recommend that you go look at that. And then Mr. Berry, if you want to add anything.
Well, I know both Ron and Dennis, so I could let them duke it out. For doing exoplanet stuff, Astro Image J is a great it's probably the way to go because so many people are using it as a standard. In terms of putting together this talk, I don't have an inside line on how Astro Image J does its computations. I think the code is publicly available. But I wanted to talk about something where I knew exactly how the thing works.
Right.
But as I said at the beginning, there's only so many ways to do this. I mean, you're going to have to slice and dice the image certain ways. You're going to have to do certain things. No matter what, you're going to try to capture what's in the central area. You're going to try to accurately handle the sky. And, you can debate from now until, doomsday as to what is the exact best way. One of the things that AIP for Wind has in it is the ability to make synthetic star images. Okay, it's one of those relatively, I think it's in the edit menu, but you can make a synthetic star that has exactly 10,000 ADUs in it. And then you can run your photometry on it. And this is how I validated the routines that I have. I built artificial stars and then tested against the artificial stars. Now you say, well, wait a minute, maybe you made errors in writing that code. That's true. But how do you validate stuff? You test and then you test it against what you think is working right. And to go back again, this particular code, the way that I showed you, is not efficiently written code. It was written to be very clear, very testable. Okay, you can look at that code and you can in your mind say, how does that work? Is it doing exactly what I think it does? As a programmer, you like to be clever, okay? You like to do things very efficiently. All that thing where we go through and we sort through the individual pixels, we do the same thing over and over and over again. You don't have to do it all over again. We could have stripped these things out. We could have put them into other arrays. We could have cut the amount of computation. But when you figure that your computer is capable of doing like 1 million operations a second of this sort, you still can't see usually between the time you hit the click and the time it appears on the screen. You can't see those processes happen.
Yeah. All right. Thank you. Let's go to the question from Dennis Conti, which was, since the AAVScope uses an alt-azimuth mount, and there's therefore image rotation, are there significant systematics introduced from this image rotation when you're doing long stacks with the AAVScope?
I have not done a careful test of that. It's a good question. But let's put it this way, what I've done with the EV scope is I'm using their stacked images here for illustration purposes. When I've done photometry, I've gone back to the individual frames and done the photometry on them. And my code knows how to, okay, not in the single star photometry tool, but in the other, it has what I call a track star or a guide star. You designate the guide star, actually 2 guide stars, and it will follow. And as the frames rotate, it will centroid and follow the stars of interest.
Okay.
Um,
Okay.
so, but I mean, I could pull up a photometry run I did on star XX Cygni, for example, where you're shooting 1 frame every 4 seconds for 4 hours. You get 3,600 data points, and it's noisy data because they're short. The star was fairly dim, but I don't see any systematic things happening. What the weirdest, the trick with the AV scope is it's a Bayer array filter. Okay, so it's a color camera. In the images I've shown, I have de-Bayered them using equal weights on the red, green, and blue channels. I haven't yet done the thing where I've split the images into red, green, and blue images and then carried out photometry separately on them.
I remember Dr. Harris talked about that method in her DSLR talk last year.
Yeah, I mean, this stuff gets complicated. If you, let's put it this way, if you can, you want to use a monochrome filter.
Right.
I mean, a monochrome camera with
yeah.
filters. If you have the EV scope as the scope you've got, you know, being a curious person, you figure out what the heck the thing can do. I've been surprised at how good it is.
Okay, we have time for just a couple more questions, probably about 5 minutes or so. So let's try and
okay.
Let's do these. So one of these is, are you self-taught in programming? And if so, what learning material did you use and or would you recommend?
I'm so old that I learned how to program with Algol 60 on a mainframe computer. Okay, so and Algol 60 is remarkably similar to BASIC, or at least at the level I understood it. I got MS Basic 5 for a CP/M computer, and that was my first experiences writing. Well, actually learned my first computing with a mini computer with 4K of memory. 4K of memory was a Hewlett-Packard, I think it was 11,000 or something. It had 4K of memory, used a teletypewriter, and I wrote software for reducing photometric results done with a photomultiplier tube. And you had a teletype terminal to communicate with the machine. Then there was a program called Turbo Pascal, and it was the first structured programming I did. And so I bought Turbo Pascal for $80 or whatever it cost, and learned how to program in Turbo Pascal. Then Microsoft introduced Quick Basic, which was structured BASIC. So I went back to BASIC. Then I switched into Visual Basic for DOS. And I wrote a lot of software for doing photometry and image sharpening and stuff like that, and Visual Basic for DOS. And the first stuff I did with photometry was probably done in that code. And I think people like Phil Sullivan probably were relatively early adopters of Photomet and Astromet, which were programs for doing photometry with images.
Mhm.
That goes way back. So I think the answer is, yeah, I'm self-taught. There was no classes in programming back
Huh.
then.
Wow, that's an impressive history for sure. Um, if you'll allow me to put in a little bit of a plug here, at the end of this year, we have scheduled 4 how-to hours, which will be focused on teaching people how to program in Python for the purposes of manipulating astronomy data. So to the person who asked that question, make sure that you come back later this year. We're going to be starting with the basics and going up through some really cool data visualization stuff using Python as a language.
Yeah, and I think if I were going to do one thing, probably in a new clean release of AIP, it would be to put out CSV files instead of photometry, so that you would be able to run your photometry in AIP, but then do your analysis any way you wanted to, by using pandas to suck in the data and then doing the photometry, writing the code.
Yeah. Yeah, that would be convenient to have it be portable in that way. Okay, we have time for exactly one more question. We're going to take this one from Mark Boderiff, who asked, is there a way to use AIP for Win to get the numerical pixel values in a subset of an image? The scenario is that if I have a star on the background of a nebula, or maybe a active galactic nuclei in a galaxy, I'm going to need to be able to do some additional math in order to get a good PSF on the point-like object.
I'm trying to remember whether there's an export function for putting out array values. I don't think so, but I'm not 100% sure. There's stuff buried in the code that is, try dig into the menus and see if you can find it. It should be there. It would have been there in the earlier code as a teaching tool. And basically, in this box, dump the data into an Excel type format.
Right.
But we might have eliminated that at some point because nobody used it.
Right. It is a little bit of an edge case. I will say to Mark as well that that would be something that would be very simple to do with Python. So I suggest you look into using Python and then a package called AstroPy with just a couple short lines. Using AstroPy, you can load an image and then export the pixel values for a subset of that image. And so look into it yourself. And then if you'd like to learn some more about AstroPy, we'll be covering that at the end of the year.
Yeah, you can probably find stuff. I think AstroPy has very good documentation, and there's probably a Jupyter notebook or Jupyter notebook with examples already written in it.
Yeah, I believe so. Okay. Now, most of what's left in the Q&A box is comments from people saying, wow, thanks so much for this wonderful presentation. Like this person said, it's inspiring me to try to do some photometry. So I want to second that, and I want to say thank you for such a wonderful and informative presentation and Q&A. Thank you for staying on extra for that.
Oh, you're welcome. And I have to remember, there's several bugs in the things there. I got to fix that. That minus 2.5. Remember that is important.
Okay, I'm going to go ahead and put up our closing slideshow.
Okay.
There we go. I guess it's just the one closing slide. Okay, so to begin our closing announcements, I want to go ahead and thank again our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology, as we talked about this afternoon. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving the scientific and technical communities in their pursuit of the scientific endeavor. Their product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and, of course, astronomy.